In this video, we will talk about a problem in the shortlist of the IMO 2019. This problem was proposed by Nigeria. The problem asks us to find all triples A, B, and C of positive integers such that a cubed plus b cubed plus c cubed is equal to abc squared. So that's a problem. This is a diophantine equation, an equation seeking integer solutions. Okay, as usual, let's first talk about the idea of the proof, the idea of the solution. The idea is that first we note that this equation is symmetric with respect to A, B, and C. So we are free to permute A, B, and C without affecting the solution set of this equation. So without loss of generality, we may assume A is bigger or equal to B and B is bigger or equal to C, and they are all positive. Is a solution to this equation. Okay, now suppose the thing has a solution ABC with A greater or equal to B, B greater or equal to C, and we will see what happens to this equation. The problem asks us to find all triples. A typical trick in solving diophantine equations is that we will try to find the range for each variable. Here, C is assumed to be the smallest one. So why don't we just start with C? The trick is that we're going to play with this equation as well as this relation to establish lots of inequalities involving C. This process might be tedious because at the beginning, you might establish lots of inequalities that are completely irrelevant. But don't get too frustrated. Just keep going. Because this problem asks you to find all triples of such. Usually there are only finite many. You shouldn't expect too many choices for C. So it shouldn't be hard to find an inequality that gives very few values for C, such that ABC is a solution to this equation. So hopefully there are not many choices for C. Okay, now we start the proof. Assume ABC is a solution with A greater or equal to B, B greater or equal to C. Assume this is a solution. Our first observation is a trivial one. We'll give a trivial inequality. A cubed plus B cubed plus C cubed. This is the trivialist squeeze between A cubed and 3 times A cubed. This part is due to the fact that B, C are positive integers. And this part is due to the fact that A is bigger or equal to B and A is bigger or equal to C. Our assumption. We are talking about this sum because since we assume ABC is a solution, this guy is precisely equal to ABC squared. So simplifying this, we get by canceling a squared out in the inequalities, this is 3a greater or equal to b squared c squared greater than a. Okay, good. We have found a good relation involving c. Okay, now let's look at the sum of b cube and c cube. This is equal to a squared times b squared c squared minus a. We are just rewriting this equation. This is just the rewriting of the equation. Because of this relation, we know this part must be greater or equal to 1. It follows that this b cube plus c cube will be greater or equal to a squared. And so, okay, now we're going to find an inequality that only involves c. We're going to start with this inequality. This inequality will give us, if we take the square, this will be 9a squared greater or equal to b raised to the power 4 times c raised to the power 4. In order to get rid of this a, we look at this inequality. This inequality will give us this 9a squared is less than or equal to 9 times b cube plus c cube. Okay, now we're going to get rid of b. How do we get rid of b? We can get rid of b by the relation that b is greater or equal to c. On the right hand side, you get this guy is bigger or equal to b raised to the power 3 times c raised to the power 5. But on the left hand side, you get this guy is less than or equal to, now because b is bigger or equal to c, this guy is less than or equal to 18 times b cubed. Okay, now great. We can cancel b cubed from both sides. This gives us 18 greater or equal to c raised to the power 5. But remember, c is an integer, a positive integer. How many choices do we have for c? Only one choice, c equal to 1. Because if c is equal to 2, then 2 raised to the power 5, that is 32, which is already bigger than 18. That's bad. So the only choice for us is c equal to 1. Good. So now the original equation becomes a cubed plus b cubed plus 1, because c is 1, equal to ab squared. C here is 1. This looks much simpler. Of course, we have assumption that A is still greater or equal to B. Okay. With C equal to 1, how many solutions do we have for this equation with assumption that A is greater or equal to B? How many solutions are there? To solve this equation, we'll first make an observation that A must be strictly bigger than B. Because otherwise, if A is equal to B and we'll get 2 times B cubed plus 1 equal to B raised to 4th power. But we cannot have any positive integer solution to this equation. This is a single variable equation. This is pretty easy to check because the right-hand side grows much faster than the left-hand side when B gets bigger. So you just test with some small values of B, and when B gets bigger, this is obvious. It will be obvious that the left-hand side is less than right-hand side. So we can test with first B equal to 1. Of course, B equal to 1 is not the solution. 2 plus 1 is bigger than 1, not equal. Now B equal to 2. What happens when B is equal to 2? This is also not an equation because right-hand side is 16, left-hand side is 1 plus 16. Now what about the case when B is equal to 3? When B is equal to 3, right-hand side is 81. But the left-hand side is 1 plus 2 times 27. Still they are not equal. And we just keep going. I think starting from B equal to 4, the right-hand side will be bigger than the left-hand side, obviously. So now you can assume A is bigger than B, bigger than 0. And look at the solution set to this equation. We first observe that this relation implies that A cubed minus B cubed, this is bigger or equal to B plus 1 cubed minus B cubed, which is strictly bigger than 1. If you multiply this out, you will see immediately this is bigger than 1 because B is a positive integer. So, as we did in the previous case, we're going to find some inequalities squeezing. Now, we have fixed C equal to 1. Now we're going to find the range for B. So now we're going to squeeze B. Specifically, what we are going to do is that we're going to look at now A cubed plus B cubed plus 1, the left-hand side of the equation. This guy is squeezed between A cubed and 2A cubed. This part is from this inequality. And this part is trivial. The thing in the middle, because a being a solution. So this part is equal to ab squared. Again, we can do some cancellation here. By canceling out a squared, we're going to get 2a greater than b squared greater than a. Okay, we get a good inequality similar to this. And now we're going to establish an inequality that only involves b. How? We're going to look at this equation. We're going to move this a cube to the right hand side. So we'll pull out a squared, and this gives us b squared minus a. Because b squared is bigger than a, so this guy will be bigger or equal to a squared, which is, by the first inequality here, bigger than b raised to the power 4 divided by 4. We're taking the square of the first inequality here. So this part is by this, and this guy is from here. Now we obtained an inequality that only involves b. So if we simplify this, so how many b's are there to make this inequality hold? B cannot be greater than 4. Because if b is 5, then right hand side is already bigger than 4. So b must be less than 4. And from here, we're only going to have 4 choices for b, which is b equal to 1, 2, 3, or 4. There are only 4 choices for b. And now we are ready to finish the solution to this equation. We're just going to plug this back into this equation and see how many choices do we have for a. So we perform this transform again, and observe that from this equation we have a square must divide b cubed plus 1. This will save us some effort later. And we're going to test it with b equal to 1, 2, 3, and 4. When b equals 1, 2, 3, and 4, b cubed plus 1 will be equal to 2, 9, 28, and 257, respectively. So you can check. But the values of a squared, what are the squares in integers? They are 1, 4, 9, 16, 25, 36, next is 49, and 64, and next is 81, and next 100, next 121, and next 144. I think that is all we need. Now we're going to check how many a squares here could divide those b cubed plus 1. Don't forget that a is strictly bigger than b. So because b starts from 1, a cannot be equal to 1. A has to be bigger than 1. So we can cross out this case. So now if b is equal to 1, then b cubed plus 1 is equal to 2. So there are no solutions A. If b is equal to 2, then 2 cubed plus 1 is equal to 9. In this case, we have a solution, which is the case when a is equal to 3. And there are no other solutions. And if b is equal to 3, then b cubed plus 1 is equal to 28. How many square divisors are there? We won't have 4. But this solution is illegal, because a has to be bigger than. This implies that no solution. And next, if b is equal to 4, then b cubed plus 1 is equal to 257. And how many cube divisors are there? I guess in this case, none of them could be a square divisor for 257. So there's no solution. Okay. This tells us that ABC equal to 3, 2, 1 is the only solution to the equation a cubed plus b cubed plus c cubed equal to abc squared, with the assumption that a is greater or equal to b, b is greater to c. So this is the only solution under this assumption. Now without this assumption, what are solutions to this equation? The only solutions to this equation will be the permutations of 1, 2, and 3. And there's going to be 6 of them. But that is not too important. Anyway, we have solved this problem.